Tak, zaczynamy się chyba. Ale tak, żeby się automatycznie nie zmieniało sobie. Automatycznie automatycznie się zmienia? Tak.
Dziękuję.
Nie będzie wyglądało.
Good afternoon, everyone. It's my pleasure to welcome Krystian Iłkiewicz, now from TANK. He's going to tell us about symbiotic stars. Krystian was working here at this observatory, and before he spent some time in the UK, but also in the United States. And he did your PhD at TANK, right? So working on symbiotic stars. So the floor is yours.
Thank you. So first of all, let me thank all of you for making me feel welcome for the last 3 years. And today I want to tell you a bit about what I was working on while staying here. So I will talk about symbiotic stars. Symbiotic stars are very fun objects. They can have jets, various kinds of outflows, outbursts, and so on. But what are they really? They are just a binary star consisting of a cool giant and a white dwarf. And white dwarf is accreting matter from the red giant, typically through wind accretion, but sometimes through Warsaw overflow. They are very similar to cataclysmic variables. The only difference is that the cataclysmic variable, the donor, is main sequence star, and in cataclysmic variables always we have Warsaw overflow, but it's very similar in that we have accreting white dwarf. The difference, the main observational difference are orbital periods, which in cataclysmic variables are of order of hours, and in symbiotic stars, the orbital periods are of order of dozens of years. From my point of view of what I study, I want to study the accretion processes. So cataclysmic variables are a bit easier because, as you can see here in the spectral energy distribution, the accretion disk dominates. Here, accretion disk is the dotted line. It dominates the optical and even infrared range. So it's really easy to study accretion then because we see basically the mass flow, the accretion. In symbiotic star, the situation is much more complicated. And you can see a spectral energy distribution of a typical symbiotic star here. So in blue, we have white dwarf. With green, we have nebula. So we have red giant that has high mass loss through wind. The wind is being ionized by the hot white dwarf, which heats up the wind and makes it emit with a nebular spectrum, and have also red giant contribution with the orange line. And as you can see here, there is no accretion disk because you cannot really see accretion disk directly in the symbiotic star because it's so faint compared to the very luminous red giant. So studying accretion in symbiotic stars is much more complicated. And this is important because for cataclysmic variables, we really understand their evolution. We can simulate it very well. And in symbiotic stars, opposite is true. You can see here the green area is orbital period distribution of symbiotic stars. And the other lines are various predictions of systems with white dwarfs. And as you can see, symbiotic stars are right where we don't expect any systems with white dwarfs from theory. And we know this discrepancy is directly related to symbiotic star phase of evolution, because these theoretical predictions are made based on population of direct progenitors of symbiotic systems. So systems with red giants, which will turn into white dwarfs. So it's not that we don't understand evolution previously, it's just that directly we don't understand symbiotic stars and that phase of evolution. And here you can see a zoom, and the red dashed line is our observational limit, because in the past we thought, okay, maybe the orbital periods are of order of dozens of years. Maybe our detection limit is too short. We don't have enough time span of observation to detect the orbital periods. And some people expected that when we push that limit to the right, the distribution will start increasing. So these would be some fringe systems. And when theory predicts symbiotic systems, you will see a race when we get longer observation. But now we know this is not true. Even though we push our limit, the situation stayed the same. So it's not that there is something wrong with observations. It's just we don't understand the evolution of symbiotic stars. So how we can study the accretion? Because accretion is really, we don't understand the evolution because we don't understand mass transfer and accretion, because that mass transfer shapes the evolution of these kinds of systems. And we can do that. We can study accretion by studying the effects of accretion. So when white dwarf is accreting mass, the hydrogen accreted accumulates on the surface until critical pressure is reached, and thermonuclear runaway will start, and we will get classical nova eruption. When the hydrogen is burning on the surface and mass is ejected, and one of the cooler systems, in my opinion, that had classical nova explosion is Eric's pop. You can see the classical nova started in the 1970s. It was very long outburst that finished roughly 10 years ago, and it's very long compared to typical classical nova that you often see, because this typical classical nova outburst lasts for days sometimes, and this is decades. And the difference comes from the fact that in this system, the white dwarf is low mass, so it takes longer time to accumulate. It takes more mass to accumulate to reach this critical pressure. So when you have low mass white dwarf, we need more time to accumulate the mass, and there is more mass, so it burns for longer. So that's why the low massive white dwarfs have longer outbursts, and typical outbursts that you see are faster because there are more massive white dwarfs. So Eric's pap again, outburst in the 1970s, and he went and looked at the neighborhood with narrowband imaging. So Eric's pap is in the center, and blue here is narrowband O3, forbidden line. Red is H alpha, and green is just broadband R filter. And first thing that you can see is on the right, there is a huge red area, and this is just unrelated H2 region. So just they are aligned in this in the line of sight. It is aligned in the line of sight, but it's not related to the object. But here you can see bright blue arc that we didn't really know what it is. And also there you may not see very well here, but there is a large ring just consisting of H alpha. That may not be visible very well, but it's there. And this ring also seems not related to H2 region because it looks like a bubble coming out of the H2 region. And first I will concentrate on this smaller arc that is bright in O3. We did spectroscopic follow-up with those, and the blue lines are our slit orientations, and the red regions are where we extracted spectra of this arc. So here you can see the arc on the H alpha image. Again, on the right is H2 region. And here is the same on O3 in O3 filter. And you can see there is a lot of structure in this arc, various knots, and so on. And first thing that you think when you see knots looking like that, it looks kind of similar to nova ejecta, because when you have classical nova eruption, the mass is ejected and it tends to form knots, various knots in the ejecta due to instabilities in the ejecta. And this is what a typical spectrum of this arc looks like. You can see forbidden O3 emission, H alpha, forbidden nitrogen, and forbidden sulfur. So this, when you are familiar with emission line spectra, this looks almost like anything. This could be planetary nebula, nova ejecta, even some H2 regions look like that, because these lines are very common among all astrophysics, AGNs. These are very common in all emission line objects. So we need to classify this object using diagnostic diagram. So you can see an example of a diagnostic diagram here. On the bottom, on the x-axis is ratio of nitrogen to H alpha, y-axis is ratio of O3 to H beta, and these various points in different colors are different regions of the arc. And here is the lines that people use to separate objects. And they were developed because people were looking at some galaxy. They saw a lot of emission line objects, and they wanted to know whether they are looking at H2 region, supernova remnant, and so on. So that's how they were developed. But the main thing to get out of this diagram is that most of the points do not fit H2 region. So this shows this arc is not related to the H2 region, but likely to Eric's Papis itself. The fact that it fits supernova remnant, it doesn't say it's a supernova. Obviously, it's not a supernova remnant. It just says that the line ratios are consistent with a shock in the emission line region, and shock is just because there is a fast outflow moving through interstellar medium. So it's not obviously a supernova remnant, but all of these line ratios are consistent with what we expect from the nova ejecta. This is another example, different diagnostic diagram, same thing. Most of the points do not fit H2 region, but either a planetary nebula or supernova remnant, which again you expect from a nova remnant. So we can say this arc probably is another nova, is a remnant of another classical nova eruption that was before the 1970s outburst. And now we want to calculate how old is this nova remnant. So this is narrowband imaging from 2016. You can see the nova remnant, and the blue line is where the nova remnant is. And this is archival observation from supercosmos from 1998. And you can see it's a bit closer to Eric's Papis in the top right. A bit over. It moved. So we can, since we observe the arc moving, we can calculate the expansion velocity, and it's this value. And now question remains, okay, it's this, the expansion velocity is equal to that right now, but people are assuming that when you have nova shell expanding in the interstellar medium, it slows down, right? It sweeps up the interstellar medium, and by conservation of energy, it has to slow down because it picks up more mass. And This is the most recent paper on the topic of change of expansion velocity. And here different colors are different nova ejecta. And you can see up to 120 years, it seems that the expansion velocity is constant. So it's contrary to what people believed before, that nova ejecta slows up with time. It seems that up to 120 years, the expansion velocity is constant. And this arc, my arc expands with this velocity. Okay, let's compare whether it's the same to the 1970s outburst. In the 1970s, the expansion velocity was this. So these values are consistent. And when we calculate the age assuming constant expansion velocity, we get the age of 1300 years. So it seems that even for 1300 years, the nova ejecta doesn't slow down. We don't really understand why, because logically it should slow down, but it seems that it doesn't pick up enough interstellar matter on the way to slow down. Okay, so this is really old nova shell, turns out. So this arc is 1300 years old, and this shell, half shell, which you don't see clearly on the screen, but has very similar morphology to this arc. And based on that, we think it's even older nova shell. And assuming the same expansion velocity, this is 7,000 years old. Unfortunately, this arc is too faint to get any spectroscopy. So I assume this is another nova shell, but to really prove that it is, we need spectroscopy. So bigger telescope than 10 meters, probably. So turns out we had 3 recorded outbursts. If we assume the shells are from previous nova explosions, in the 1970s, 1300 years ago, 7,000 years ago. So this needs the recurrence time change from 1200 years to 6,000 years roughly. And this is very large difference, right? So there are 3 ways to change the nova recurrence time. One is change the mass of the white dwarf, which you cannot do on that time scale. Second one is change mass transfer rate, which seems plausible. And the third way is change the core temperature of the white dwarf, which you can do, but this is the least significant parameter, and you cannot realistically change temperature so much that you would observe this dramatic of a difference. So most likely, on the time scale of last 10,000 years, mass transfer rate had to change in this system. And by comparing to theoretical models of nova eruption, the mass transfer rate had to increase by a factor of 3 in the last 10,000 years. Why 10,000 years, not 6,000 years? Is because the mass had to be accumulated before the nova explosion. So this is the first time we can more or less accurately, and using some assumption, measure the mass transfer rate change on time scale of 10,000 years, which is really cool. Because it makes it easier to predict the evolution and compared to evolution models of binary evolution and the evolution of mass transfer rate predicted by theory. And you may wonder why it changed by a factor of 3. It's just the red giants evolve very fast on this, and the red giants, similar to as in Eric's path, they evolve very fast, and the mass loss through wind changes by similar factor on these timescales. So the mass transfer change is due to probably due to changing the wind strength of the red giant in the system. You may say, okay, it's not really interesting. We already knew the wind changes in similar system, but we can directly compare how changing the mass loss of a red giant predicted correlates to mass accretion rate because they not necessarily have to be one-to-one because we need the result of hydrodynamics and so on. So it's really a cool system to compare and push our knowledge of theoretical models. So another hot topic important for discussion about symbiotic stars is a new so-called hidden symbiotic stars that in recent years appeared in the literature. So what is a hidden symbiotic star? A normal symbiotic star is just a red giant spectrum, so a lot of molecular bands in absorption and a lot of emission stars, because again, emission lines, because again, the wind of the red giant is being heated up and ionized by the hot white dwarf. And this is the first hidden symbiotic star discovered. So you can see here a spectrum, and it's just basically no emission line, just a red giant. Here is a zoom on H alpha. There is a tiny H alpha in emission, but you wouldn't classify this object as a symbiotic star based on that, because we assume symbiotic stars are interacting binary stars, meaning they have to interact, meaning there is a lot of accretion on the white dwarf. And since when you have a lot of accretion on the white dwarf, it's very hot and it heats up the nebula enough to have strong emission lines. And without strong emission lines, we say it's not interactive. But it's a topic of discussion in the community. What do we think about these hidden symbiotic stars? And it's very problematic because H alpha in emission lexing here, that is very tiny, can be seen in single red giants, because when red giants pulsate, sometimes there are shocks in the atmosphere that cause emission lines in the spectra. So it's very controversial kind of system, class of systems now, but this is the first one and the most important one and best studied. And why people think it's a symbiotic star, even though it doesn't have emission line, that it had like a high state in X-rays, meaning there has to be some accretion probably, since there was a high state in X-rays. So what I did, I looked at the optical data, and basically in optical is flat. The gray area on the left is where there was X-ray high state. The red line is when the system was reported and there was follow-up. And the blue line is where I found the spectrum from some French survey topic. And so it's right in the middle of the X-ray high state, and this is the black line here. So when the system was X-ray bright, the H alpha was very strong in emission. And it looked like a typical symbiotic star shown here in the gray line. And now, when the X-ray intensity is low, it looks like that shown here in the red line. So now it doesn't look like a symbiotic star, but for a very short time, it looked like symbiotic star. And this is also shown here. You can see H beta equivalent width is dropping. And only at the beginning, when the first point on the graph here is located, you would classify the system as a symbiotic star. What else? I discovered the P-Cygni profile. So P-Cygni profile basically means we have outflow from the system. So not only it was bright for a short time, there is an outflow, so probably something happened that caused accretion and outflow for a short time. And here you can see change in sodium B1 line. It grows and then goes down. And this basically is correlated with reddening of the system. So the bigger the equivalent width of sodium, the more reddening. So compiling the P-signal profile, we can say there was some outflow from the system, it obscured the binary, and then it drops down, so it expands and the reddening goes down because of the expansion. So this, combining all of this, we can say SU Lyn is not a hidden symbiotic star, it's a transient symbiotic star. So it was a symbiotic star for a very short time. And why it experienced accretion only for a short time, probably it's either of two explanations. Either it's in an eccentric binary, so we have eccentric orbit, and only when the white dwarf is closest to the red giant, in the eccentric orbit, there is accretion, or there was some dust ejection event from the red giant, which happens sometimes, right? So either two explanations, neither of which are that very interesting. What is interesting is I fitted the stellar parameters of the red giant. So here it's showing the red lines. You have evolutionary models, and the gray line is the best fitting evolutionary models. And this shows that the red giant is very early in thermally pulsating phase. So probably it experienced its first thermal pulse, so helium flash. And this is how we expect to change, how the mass loss from the red giant will change in the future. And you can see in the next few years, we expect it to increase very fast. So this is from the best fitting models, but this would mean that the system will experience an increase of mass transfer in a time scale of the next 100 years. So basically, within our career length, we can observe this system becoming, we can observe how it will become a normal symbiotic star, because the quiescent mass transfer rate is 1 order of magnitude less than in the normal symbiotic star. So we only need to increase the mass loss by a factor of 10 for it to show emission lines and become normal symbiotic star. So why it's interesting? It will become, models predict it will become a symbiotic star in the next 100 years. So why it's so interesting is because one of the most famous symbiotic stars is CH Cygni, and it's famous for various reasons. One is that it launches jets, and see here it's jet. So it's very famous, very well studied, one of the best studied symbiotic stars. But the point is, 100 years ago, it was not a symbiotic star. So actually, it was used as a spectral type standard. So it was typical, so typical red giant spectrum that people use it as a standard for all other red giants. And only roughly 50, 70 years ago, something like that, it showed emission lines and became a symbiotic star, and it is symbiotic star since then to now. So by observing SU Lyn, this increase in the next decades, we can see how a star becomes a symbiotic star. So it's a very interesting object for the future, for the younger people to observe. And when we observe how it becomes symbiotic star, maybe we can then see where our evolutionary models are wrong. Okay, so let me switch the topic a bit. Yeah?
Case of the Cygni, you know the period, it's like the 200 states.
It's a bit controversial.
Cannot exclude the variation.
It's symbiotic in CH Cygni, it's 15 years, I think the most well accepted, but there are some people say it's a triple, I don't want to comment. But it's not that in CH Cygni for sure it's not a very strong process. Okay, so the most hot topic in symbiotic star research now is T Corona Borealis, and you can see Corona Borealis experience nova outbursts here and here. So there were two here. And what is interesting, what keeps people's attention is that it increased in brightness just before the last outburst. And now it's also increased in brightness similarly. So using that, people are predicting it will explode in actually they predicted September last year, but it will explode soon. So here is a zoom. You can see this, the most recent variability looks very similar to this. But what got my attention is also that we see also other brightenings over the years that are not very well studied. Why they are not very well studied? So here is a short part of this previous side curve on the bottom, and in the middle we see light of EU, and in the top equivalent width of H alpha. So as you can see here, the variability is best seen in equivalent width of H alpha and almost invisible in B. There is short-term variability on top of that from orbital motion, but this long-term variability on timescales of thousands of years is only visible in very blue filters or in spectroscopy. And this prediction is based on basically V filter. Yeah. So when you look at just the spectroscopy, so equivalent of H alpha, variability here, the amplitude of it looks exactly like variability here. So it's just we don't have good data enough in between outbursts, and not that the last increase in brightness is so much bigger. It's just we didn't have good data. But also when you look closely, the big increases in brightness are far apart, but in between them we have shorter and with smaller amplitude increases in brightness, which for me, when I look at that, looks very similar to SU type dwarf novae. So dwarf novae is different from classical novae in that in classical novae we have outbursts, thermonuclear runaway on the surface of a white dwarf, and dwarf novae is thermal instability in the accretion disk. So it's only the accretion disk that drives the change in brightness, and in SU type dwarf novae, you can see smaller outbursts and sometimes longer, bigger outbursts called super outbursts. So this for me looks very similar. So I took that, the data from the last 50 years, roughly. I removed the red giant contribution and smoothed the light curve, and it looks like that. So you can see with blue lines, I marked the big amplitude changes, and with red lines, smaller amplitude. So let me note that here it doesn't look that well, but I also combined UV observation, spectroscopic observation, and so on to derive the times. I calculated the amplitudes of the big outbursts and small outbursts and the recurrence time, and I compared them to dwarf novae. So on x-axis is the smaller so-called normal outburst amplitude, on y-axis is the bigger super outburst amplitude. The gray and black points are different kinds of dwarf novae, and red is T Corona Borealis. And as you can see, it fits the relation for dwarf novae very well. Here is something similar on the recurrence time. So this is the big outburst recurrence time on y-axis, and on x-axis is the smaller outburst recurrence time, and it also fits. So this shows that this variability is really just SU type dwarf nova. So instability in the accretion disk. Also, X-ray behavior is consistent and so on, but I will not get into details. Also, what is similar is you can see why there are super outbursts. Let me first explain. So here are normal outbursts and big super outbursts. Big super outbursts is because with each dwarf nova outburst, the disk is a bit bigger. And when we have super outbursts, it reaches the 3-to-1 resonance distance. So there is a 3-to-1 resonance between the accretion disk and the donor. And this becomes ellipsoidal. And because of that, we see big super outbursts. And during super outbursts, we see the precession period of ellipsoidal accretion disk. And something very similar is seen in T-corona borealis, where during this big super outburst, we see sinusoidal variability similar to the super humps of the precession period of the accretion disk. So it almost, for me, is clear that variability in T-corona borealis is dwarf nova. And why it's interesting? It's because we never saw dwarf nova in so big accretion disks. We only saw them in cataclysmic variables, which, as I said before, the orbital period is of order of hours. So the system is tiny, and symbiotic stars have orbital periods of order of years. So very big orbitals.
Those are the shortest.
Sorry?
200 days.
The orbital period. And this would be, in my interpretation, precession period of the accretion. And there were theoretical predictions of dwarf nova outbursts in symbiotic stars, even though none were observed. And turns out they are consistent with what I measured. So it looks like a dwarf nova is consistent with prediction, so it is probably a dwarf nova. And the fact that there was no classical nova outburst related to in my interpretation, super outburst is consistent with that. So why it's interesting is because dwarf novae were observed cataclysmic variables with rotation this big. AGNs have accretion this big. And symbiotic stars are here. So on logarithmic scale, they are closer to AGNs than to cataclysmic variables. And it's really interesting because a lot of people, for example, in this paper, on this paper, try to predict dwarf nova outbursts in AGN disks, but no one knew whether dwarf nova outbursts can happen in accretion disks larger than cataclysmic variables. So T-corona borealis proves that at least they can happen in accretion disk halfway there on the logarithmic scale. So it's really cool that we can use binary stars to push accretion disk physics for AGNs. So what is also interesting in T-corona borealis is fast variability in X-rays. So you can see here is variability on time scales of minutes observed 20 years ago. So what caught my attention is this event, and you can see the hardest blue here in blue range. When we see decrease in brightness, we see increase in brightness in the green, so the middle range. So this for me looked like Compton scattering, but I have not been able to prove that for many years. And I wanted to, and it's one of the unsolved mysteries in the T-corona borealis, why we see this fast variability. So what I did, I went to systems similar to symbiotic stars, to post-AGB binaries. So you can see post-AGB stars where they lay on HR diagram here. So they are basically past the AGB phase. They are expelling the outer shells the star is expelling the outer shells, and it will become planetary nebula. It's in the process of becoming planetary nebula. They are in binary systems, and you can see a cartoon of such system here. So there is a post-AGB star, transferring mass to unknown object, probably white dwarf from the system star. The unknown star has accretion disk and is launching jet, but the whole system is surrounded by circumbinary disk that is formed by these outer shell ejections. And the accretion and the circumbinary disk is in the orbital plane, more or less. And I went to see whether they also show fast variability, and it turns out they did. And you can see the light curve is smooth. So this is a test light curve, it's smooth. And at some point, the brightness drops, and there is fast variability. And fast variability disappears, and the brightness goes back up. So this is, note that this is at more or less at orbital phase 0.49. This is different observation. Orbital phase 0.49, there is no variability. So the variability sometimes was there, sometimes was not there at the same orbital phase, meaning it's not connected to any geometrical effect, connected to orbital motion. Sometimes it was all over. So what's the reason behind the fast variability? The hint could be that the system experiences drops in brightness with orbital phase in general, and the dashed line here is where the post-AGB star is closest to us. And it's strange to see the brightness drop when the post-AGB is closest to us, because post-AGB star is source of most of the light in the system. So there is nothing to obscure the star other than circumbinary disk. So probably the star is being obscured by circumbinary disk. And this is similar to RVD phenomena in RVD stars, which also have circumbinary disk. And you can see they have drops in brightness. Also, the post-AGB star is closest to us and is eclipsed by the inner ring of the circumbinary disk. So my interpretation of the fast variability that was not known really before in post-AGB stars, is that since it's not related to orbital phase and brightness drops when variability appears, it's just due to clumps of matter in the circumbinary. So basically, circumbinary disk is not smooth, but we have some clumps, and when the clumps is in the light of sight, the brightness drops, then it moves out of line of sight, and the brightness increases. So that's why when the variability appears, we see a drop in brightness, because it's just because of the red. And I think similar can be used to, similar scenario can be used to explain the coronavirus variability. So this would be Compton scattering on time scale of minutes. Here is also on time scale of minutes, more or less. So we would have in the coronavirus blobs of matter on the in the orbital plane. So it's really cool, because using this fast variability now, maybe we can in the future study the structure of the circumbinary disk, which we couldn't really before. We only put, I mean, small scale structure, because before we only could observe like large scale structure of the circumbinary disk using interferometry. But now we can really go for the details. Okay, I think I will finish here. Thank you. See you.
Thank you, Krystian. Any comments or questions?
My first question is about example. You said that it's our verse is very long because the white one is low mass. I would expect that the recurrence time being that's kind of outburst, you know, white wolf mass system should be quite long. I would say maybe 100,000 years. So this is why I was puzzled why the time is pretty short, a few thousand years. So What should be the typical recurrence timescale for low mass white dwarf?
So as I said, I compared the timescales to theoretical models and to this. I don't remember first author, but Shara group and Pirani group, and I used white dwarf mass of 0.6 solar mass, and that for that recurrence time I needed 10 to the minus 8 accretion rate solar mass per year, and that then it fits models. So the model grid is pretty big, so you can find models that fit this scenario. Also the outburst is long. That's why I assumed low mass white dwarf of 0.6 solar mass. The shorter outbursts are for white dwarfs of 0.8 or 1 solar mass that you typically observe.
Okay, and another question about the curve. What if it doesn't happen? What if it doesn't erupt now?
So
I assume that you will be happy because it kind of depends your model. It's
yes, but what would not confirm my model is because Schaefer predicted that the increase is because of upcoming classical nova eruption, and he predicted September 2024.
What is the answer?
So,
what is the error?
half a year, something like that. The upper limit was so September or earlier was the original prediction. So I'm happy it didn't happen then because it's more in favor of my model. But of course, it should go out soon, just because when you take the difference between these two outbursts, that third one should be more or less here, right? So it has to go out. But my point is just that this other variability is not related. But it accretes mass, it's a white dwarf, it has to go out, unless, of course, it not necessarily always happens like in AG Pegasi, which experience classical nova outbursts, and then it will not again because during the last classical nova eruption, the hydrogen burning never stopped, so it's a stable hydrogen burning system now, but we don't see any change in the mean brightness since before last addition, after, so I doubt it's the case here.
Anyway, you expect the classical outburst.
It accretes mass, it's a white dwarf, it's not stable hydrogen burning, has to do something.
Okay, so there was a similar behavior in case of the other classical novi. This high stage accretion. Also could be like this.
Also could be. I think you had the paper on something similar. Yeah. So the problem is that, as you can see here, it's the optical is not very well pronounced, the variability, so it's hard to get good data to pinpoint exactly when each active state starts and ends. So usually I used UV or spectroscopy, but not all systems have that good coverage as the coronavirus. But it's a topic for future stuff.
Yeah. More questions?
So you're looking for the satellite behavior in case of the AGN?
So the problem is that in AGN, the timescales are so big that you would not reasonably be expected to see the actual change due to outburst. How people try to look for that is just at the distribution of luminosities of AGNs, and statistically saying, okay, this statistically these AGNs are on this stage of outburst, these are on this stage. But as I said, currently there is not much interest in the community because most people don't believe.
But this quasi-periodic oscillation connected in this precession.
No, but you wouldn't expect in case of AGNs because the super hams, so this fast variability comes from the 3-to-1 resonance with the donor.
Okay, no.
And in AGNs you don't have it on.
But you can have something.
Maybe.
So do we have any questions or hands on Zoom? How to get back to the.
Mariusz, I think you have
No, I just wanted to see if there's how to get back to the Zoom menu. I don't think there's any, but just to be sure. Are we hide there? Yes.
Okay, no question.
Okay. So let's thank Krystian. Thank you very much. And we'll use this opportunity also to introduce new people in our institute. We have a new PhD student, Zofia Bucik, who's working with Radek Poleski on microlensing events. And we have also a new postdoc, Surajit Kalita, who's working with Tomek Gulik on gravitational waves. So welcome here. And we're happy to be part of our founding. Thank you very much. See you in a week. We're going to have a talk of Marek Szczepańczyk about gravitational waves. Right? Yeah. Okay. Thank you. See you.
Thank you.
Mysterious. Wyłączasz kamerkę, co?
Jest jedna gra, wiemy, że ma sobie a reszta nie ma. Nie, wszyscy.
Tak.
Ale teraz mogę się nikt lepszej roboty nie zrobił, tak? Tak. Ale szacował masę.